Okay, let's start on lesson 12.1b. So this is the second half. It's a pretty quick lesson. So the conditions, we haven't talked about these, but for performing a chi-squared test for goodness of fit. Remember, there's two chi-squared tests. We haven't learned about the second kind yet. The data comes from a random sample. So that's like we've had before. Less than 10% of the population. That's like we've had. This is different. So large counts, instead of we've had large counts for proportions, that was NP had to be greater than 10. We've had large sample. We have different ways to carry that out, but N had to be bigger than 30, or you had to draw the graph. No strong skewness, no outliers. Here, we need all of the expected counts to be at least 5. The key thing you need to know is somewhere on your paper, you need to write all those expected counts. Oftentimes, I just put it in the table. I put a slash mark next to the number that's the actual count and put the expected count right next to it. So when checking the large count condition, be sure to examine the expected counts, not the observed counts, right? So that's, you've got to write the expected counts somewhere. And sometimes the expected counts are just, all outcomes are equally likely, and so they're all going to be the same. That happens quite often, actually. Okay, this is the formula. You don't have to memorize it. It is on the formula sheet, so that's nice. But that's the formula for the sum. The sum, that the symbol sigma means the sum of the observed minus expected squared over expected. Okay, so this is one I have a sheet for. In his book, Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on the chance to make it the highest level of the game, to make the pros. Specifically, because January 1st is the cutoff date for youth leagues in Canada. And honestly, most hockey players come from Canada, or at least a big majority. Players born in January will be competing against players up to 12 months younger. So that could be kind of an advantage, especially when you're young. If you're a little bit stronger, a little bit bigger, maybe more coordinated, then you might have the advantages of getting more playing time, more coaching. You just might be more successful, right? So to see if a birth date is related, date of the year, is related to success, judged by whether a player makes it to the NHL or not, a random sample of 80 NHL players from a recent season was selected and their birthdays were recorded. The one-way table summarized the data on birthdays of these 80 players. And so right away, you can see the distribution doesn't look very balanced here. So it looks like October, December, not as popular, a lot of January through March. So that first quarter of the year, it seems to be when a lot of the players are born. So there might be some credence to this theory, but let's do the test and see what happens here. So do this data provide convincing evidence? The birthdays of NHL players are not uniformly distributed across the 4 quarters of the year. I like to parrot that back in some of our responses here. So you want to start by, talking about what's the null, what's the alternate. The null is, that birthdays make no difference. So the null is that the birthdays of all NHL players are uniformly distributed across the quarters of the year, or across the year, basically. So it's uniformly distributed. There's nothing unusual going on here. That's the null. The alternate is they're not uniformly distributed, right? And so then you want to define the, we don't have to define the parameters. There's no mu or p here, but we should state the alpha level. Somewhere on your paper, make sure to say the alpha level. Okay, so now name the type of test we're doing. So this is a chi-squared goodness of fit. It's fine to use the abbreviation that x squared. It looks like x squared. It's chi-squared GOF. That'd be fine to say. It's exactly what your calculator says, actually. Check the condition. So random sample right here, it says a random sample of 80 NHL players. I would underline that, draw a line, write the word random sample. Less than 10%, so 80 is less than 10% of all NHL players. I think there's more than 800 NHL players. And then the large counts condition, all the expected counts. So what are the expected counts here? So the formula for expected count is n times p. So we have 80 times the probability of success. We think that ideally it's one out of 4 here. So 20 would be the answer here. So for each of those would be 20. So January, March, I would put 20. April, June, 20 is the expected. That's actually what we got. And then July, September, 20, and October, December, you expect 20. So you expect 20 in each category. That's the expected value. Somewhere on your paper, you have to put 4 20s. I just put them right next to the observed count. So I put /20, 32/20, 20/20, 16/20, and 12/20. Okay, so we check the conditions. You want to do the do part then. So this is where you want to show a little bit of the work. So like this is, you don't have to show all 4. In this case, there's only 4, so they showed all the work there. But you could just show the first 2 plus ... and show the last one. So if there's like 10, don't write out all 10. It's just a little too much. You don't have to show this step, although it's nice to be able to access that information when you need it on a certain follow-up question. So show the first 2 fractions plus ... show the last fraction, and then show the answer for chi-squared, which is 11.2. Definitely write the degrees of freedom somewhere on there. If chi-squared is 11.2, you would use chi-squared CDF. It's always skewed right. It's always shaded right for chi-squared. So lower bound would be 11.2, upper bound infinity, degrees of freedom is 3, and you get a p-value of 0.011. So if you do this in your calculator, what you have to do, and I would highly recommend, let's say you've got some stuff here, so you can hit the, let me go back to the thing. If you want to hit the dock key, go to insert problem. Sometimes it's nice to do that. So then if you have previous stuff, it's not going to affect your variables. So I always call my things the same thing, OBS for observed and expect. Don't just use EXP. It thinks it's an Excel command here. And so we're going to put the 4 observed values, 32, 20, 16, and 12. And then the 4 expected values right next to it, 20, 20, 20, and 20. Okay, so now we're going to do the test. So go to home page, go to a calculator page, and let's do the test in here. So menu, stats, it's got to be under tests. And there it is, chi-squared goodness fit. It's fine to call it that on your paper, to write just those exact words. Observed is OBS. Hit tab, expect is there. And degrees of freedom was 4 categories, so number of categories minus 1, so it would be 3. Okay, and it gives you pretty much everything you know if you just write those things down. Chi-squared goodness fit, that's the name. Chi-squared 11.2, p-value. We do want to see a little bit of the work. We like to see those first couple of fractions and the last fraction there of the chi-squared value. So and this one, we really like to see the extra bit of work. It depends on the rubric as to whether they're going to call you on that or not. P-value 0.01 and degrees of freedom 3. If you want to see the comp list, that's actually really helpful. So if you hit the variable key right above the number 9 and go to comp list, you can see those are the 4 values in order. The first, that January through March, that 32 was a lot bigger than we thought. It contributed 7.2 out of 11.2 for the chi-squared. So most of the variation, or a lot of that, came from the first value there. So that's really helpful. Sometimes the question would be, which quarter contributed the most to the chi-squared value? You would say that first quarter, because that first number there is 7.2. So that's the biggest. The second biggest would be the 3.2. October through December is a lot less than we thought, actually. So that would be the second biggest option there. And finally, the conclusion, because the p-value of 0.011 is less than the alpha level of 0.05, we reject it. No, we do have evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year. And so we've just proven that we don't have enough evidence to say that, so we do reject, so we do have evidence to say that they are not uniformly distributed. We're not saying which month is better or whatever, we're saying they're just not uniformly distributed. And you can do that in your calculator, which we did. If you do that in your calculator, We recommend writing out the first few terms of the chi-squared, followed by dot, 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 and the last term. This approach might help you earn partial credit if you enter a number incorrectly. Be sure to name the procedure, chi-squared good as a fit, and to report the following test statistics. That's what I said, chi-squared, degrees of freedom. Those are the three things the calculator really gives you there. So if you want to know how different, it helps out to talk about the contributions. In other words, that's what we mentioned, the 7.2 and the 3.2 there. Those are the contributions from the comp list there. And so there were 8 fewer born, 12 more than expected. And so that's oftentimes a follow-up question, is which one contributed the most, which of the months in that case. Okay, that's your lesson for today.